Good evening, children.
Good evening, ma'am.
Good evening. Good evening, ma'am.
Good evening. Good evening, children.
Good evening, ma'am.
Good evening. All right, so let's take the introduction to this chapter, circles. So the basics about circles, what a circle is, what is radius, what is diameter, chord. So the basic introduction to this chapter you've already had in standard 9. We'll just continue with that. So now for this year, these terms secant, tangent, we have seen them in standard 9. But we will be dealing more with secants, tangents, and we need to understand the meaning of the term length of a tangent. Let's see them now. Now we know that a line has no endpoints. It extends indefinitely on both the sides. Secant and tangent are two such lines which have some relation with a circle. Secants and tangents are lines. They're not line segments, they're lines. A secant is a line. A tangent is a line. And they're called secants and tangents because they have some relation with the circle. Now, you see this figure here? There is a line PQ. Look at this figure in 1. There is a line PQ. There is a circle. There is no relation between the line and the circle. There is no relation. There is no connection between the circle. This is a circle, this is a circle, this is a line. PQ is a line. PQ is a line. And this is a circle. If I mark this, this is a circle with center O. There is no connection. There is no relation between the line, between the line and the circle. So look at this figure here in 2. If the line were to intersect the circle at 2 points A and B, the same line, this line PQ, if this line PQ intersects the circle, see the line PQ, if the line PQ intersects the circle at 2 points A and B, see here, A and B, A and B. Now, there is a relation or there is some term which is used in connection with the circle and this line. This line is called the secant to the circle. This line is called the secant to the circle. A secant is a line that intersects the circle at 2 distinct points. Now, what if the line PQ were like this? It touches the circle. It touches the circle. You can say it intersects or it touches the circle at exactly 1 point. In the third figure, the line PQ. In the third figure, the line PQ touches or intersects the circle at exactly 1 point A. And here PQ is called the tangent to the circle. A tangent is a line that intersects the circle at exactly 1 point. Tangent is a line that intersects the circle at exactly 1 point. A secant is a line that intersects the circle at exactly 2 points. What is the length of a tangent? What is the length of a tangent? Now, supposing we take a point. We'll call this tangent PQ. Now, supposing this is R. Okay, R is called the point of contact. R is called the point of contact, the point where the tangent touches the circle or intersects the circle or meets the circle. The point where the tangent or the tangent line meets the circle, intersects the circle or touches the circle is called the point of contact. So R is the point of contact. R is the point of contact of the tangent PQ with the circle. Now, R is the point of contact, and supposing I take some point like A on the tangent. Now, AR is a tangent segment. AR is a tangent segment. Now, supposing I take a point B on the tangent. I take a point B on the tangent. Now, BR or RB is a tangent segment, like how we say line segment, a part of a line. A part of a line is a line segment, portion. A tangent segment is a part or a portion of the tangent because the tangent is a line. A tangent is a line. So a tangent segment, a part of this tangent. And which part of the tangent? So it's the length between the point of contact and any point on the tangent. See, you can see this and understand. Now we said that AR. Let me clear the slide. Okay, let me call this tangent L. Okay, this is the tangent L. L is the tangent. Now P is the point of contact, and you can see the points A, R, and B. A, R, and B on the tangent. Now all the distances from P. So now PR, that is the length between the point of contact and any other point on the tangent, is called the tangent segment. The length of the tangent segment or the length of the tangent. Because sometimes, we don't use the word tangent segment. We simply say length of the tangent. Then we'll be like, tangent is a line. How can we measure its line length? So tangent segment is also said length of tangent segment. Sometimes is referred to as length of tangent. It's understood. It's tangent is a line, and you cannot measure the length of a line. So when it is length of tangent, it is the length of some tangent segment. Is understood. So here you see PR is a tangent segment. PA from the point of contact. PR is a tangent segment. PA is a tangent segment. PB is a tangent segment. So you can see the definition below. The length of the line segment of the tangent between a given point and the given point of contact with the circle is called the length of the tangent from the point to the circle. You don't have to remember this definition or something, just understand the essence of it. So this distance, this is the point of contact, and this is a point on the tangent. So this distance between the point of contact and any point on the tangent is called the tangent segment. So PR is a tangent segment. PA is a tangent segment. PB is a tangent segment. So as we understood in figure 1, there's no relation between the line PQ and the circle. In figure 2, line PQ is a secant to the circle, intersecting the circle at the points A and B. Line PQ is a tangent to the circle at A. Tangent line PQ is a tangent to the circle at A. That is, A is the point of contact. What this figure says is when you take a point P on the circle, you can draw infinitely many lines passing through this given point P. But of those infinitely many lines, only one line can act as a tangent to the circle. I'll repeat. Circle, point P, on the circumference of the circle. We know that there are infinitely many lines passing through a given point, or we can draw infinitely many lines passing through a given point. So through this point P, which lies on the circle, through this point P, you can draw infinitely many lines. Of those infinitely many lines, only one line can act as a tangent to the circle. The others will be secants. Through the point P, we can draw many lines as we wish. Of those lines, only one line can act as a tangent to the circle. So in this figure, looks like A dash P B dash. If I'm not wrong, A dash P B dash is a tangent to the circle. So A dash B dash is the tangent to the circle at P. A dash B dash is a tangent to the circle at P. We'll talk about this a little later. We'll talk about this figure a little later. This one. Look at this one. Now, P dash Q dash is a tangent to the circle. P dash Q dash in this figure P dash Q dash is a tangent to the circle. Now you can draw many lines parallel to this tangent P dash Q dash. You can see that's what they've shown here. These lines, all these lines are drawn parallel. All these lines are drawn parallel to the tangent P dash Q dash. Sorry, P dash Q dash. Correct. P dash Q dash. Now, you can draw many lines parallel to this tangent P dash Q dash. And can you see this P double dash Q double dash? P double dash Q double dash. That is the tangent. That is the tangent. See, these are lines. What are these? These are lines. These are lines or these are secants. We'll say lines now. These are lines that are parallel to P dash Q dash. And you can see that there can be only one tangent. There can be only one tangent called P double dash Q double dash that can be parallel to the tangent P dash Q dash. We have the proof, children. We're just seeing it, diagrammatically. You definitely have the question why in your mind. How can you prove this? We will be proving these results. Not all these results. These you can understand. These are enough. This is fine. This should be fine. We have a proof for this. Just trying to say what this figure is trying to convey. So P dash Q dash is a tangent to the circle. P dash Q dash is a tangent to the circle. Okay. We can draw many lines parallel to this tangent P dash Q dash. But there can be only one tangent P dash Q dash. You can draw many lines. See the usage of the words. There can be many lines or secants parallel to the tangent P dash Q dash. But in the end, you can see that there is only one tangent P double dash Q double dash that's parallel to the tangent P dash Q dash. And we'll also see that these two parallel tangents will be at the ends of the diameter. They'll be at the ends of the diameter. That is when you have a circle, and if this is the diameter, if you draw a tangent if you draw tangents at the ends of the diameter, if you draw tangents at the ends of the diameter, they will be parallel to each other. Tangents drawn at the ends of a diameter are parallel to each other. Tangents drawn at the ends of a diameter. You take a diameter. A diameter has two endpoints, right? So through those endpoints, if you call this diameter AB, there's some part is white. Through A and through B, you can draw tangents to the circle. Through A and through B, you can draw tangents to the circle. These two tangents will be parallel to each other because they're at the ends of the diameter AB. Following, children? Are we all getting it right?
Yes, ma'am.
Yes, ma'am.
Secant, tangent, all right. Length of tangent. Then what these figures convey. So here it means through the point P, many lines can be drawn. But of those many lines, only one line can act as a tangent to the circle. Because the tangent is a very sensitive line. It should touch the tangent is a line that touches a circle or intersects a circle or meets the circle at exactly one point. This one we'll see later. In this figure, P dash Q dash is a tangent to the circle at this point. We can draw many lines. Parallel to the tangent P dash Q dash. And those lines will be secants to the circle. So there are many, you can draw many secants. Parallel to the given tangent P dash Q dash. And finally, you see there is a line P double dash Q double dash, which is also a tangent to the circle. And that line P double dash Q double dash is also parallel to P dash Q dash. And it's also a tangent. So that means you can draw only one tangent parallel to a given tangent. Supposing you're given a tangent to the circle, how many tangents can you draw parallel to the given tangent? You can draw only one tangent parallel to the given tangent. So if the given tangent is P dash Q dash, then the tangent parallel to P dash Q dash is P double dash Q double dash. That's all. There is only one tangent that can be drawn parallel to a given tangent. If P dash Q dash is a tangent, then its parallel tangent is P double dash Q double dash. And tangents, this is the result. Tangents at the ends of the diameter. I'm not getting the pointer. Yeah, tangents at the ends of a diameter. When you connect these 2 points of contact, this will be the diameter. When you connect these 2 points of contact, this is a point of contact. When you connect these 2 points of contact, you will see that this line segment is a diameter to this line segment is a diameter to the circle. When you connect the points of contact, you will see that the line segment is a diameter to the circle. So tangents at the ends of a diameter are always parallel to each other. Now, you'll understand what these figures are trying to tell us. So if we take a point P inside the circle, when we take a point P, so this is about the number of tangents that can be drawn to a circle. This is about the number of tangents that can be drawn to a circle. Let's take a point P inside the circle. If you take any point inside the circle, you cannot draw a tangent passing through this point P. So here we have taken a point P inside the circle and we try to draw many lines passing through P. You will see that all these lines can be secants to the circle, but not tangents. Because all the lines will intersect the circle at two distinct points. Secant. So when you're given a point, because there's a secant, all these lines are secants because they intersect the circle at two distinct points, 2 points. So given a point inside the circle, we cannot draw any tangent, or there is no tangent that can be drawn passing through a point lying inside the circle. Now let's take a point on the circle. When we take a point on the circle, there's one and only one tangent that can be drawn. There is one and only one tangent that can be drawn passing through this point lying on the circle. When you take a point P outside the circle, we'll see that exactly two tangents can be drawn. Construction of tangents we have. So in the chapter constructions, when we construct tangents, we will see that, from an external point, we can draw two tangents to the circle, to the given circle. So in figure 3, point P is an external point. Point P lies outside the circle. And from this point P, we can draw exactly two tangents, PT1 and PT2. PT1 and PT2. We can draw exactly two tangents from a point lying outside the circle. So if P lies inside the circle, no tangents. P lies on the circle, exactly one tangent. P lies outside the circle, exactly two tangents. This fine, children?
Yes.
Converse of theorem 1 has been deleted from your syllabus. Theorem 2 or converse of theorem 1 has been deleted from your syllabus for this year. So we'll see theorem 1, 3 and 4. Theorem 1, the tangent at any point of a circle is perpendicular to the radius through the point of contact. The tangent at any point of a circle is perpendicular to the radius through the point of contact. So we have a circle. The tangent at any point of a circle, you can draw it anywhere, but for the sake of convenience, I'm going to do it here. So we take this point on the circle and we draw a tangent through this point. Tangent. This is the point of contact. Let's call the tangent AB. You can also call it L. It's your choice. Tangent L or tangent T. So T is a tangent. The tangent touches a circle, say at P. The tangent touches a circle at P. That is, we have drawn a tangent passing through P. We have drawn a tangent passing through P. Now through this point of contact, we'll take the radius. We'll take the radius. So this is the center of the circle O. We'll take the radius through the point of contact. So through the point of contact, that means from here you should join this to the center. So this is the radius through the point of contact. This is the point of contact. Through the point of contact, let's take the radius. This is the radius through the point of contact. Now this radius will be perpendicular because you can see there's a radius like this also. Radius. So the radius through the point of contact, the tangent at any point of a circle is perpendicular to the radius through the point of contact. This is the point of contact. Through the point of contact, you take the radius. That radius is always perpendicular to the tangent. The tangent at any point of a circle. You take the tangent at any point of a circle. See it again. Any point. Now supposing here. The tangent at any point of a circle. This is the, supposing we take this point A. Okay, so through this point A, we draw a tangent. The tangent at any point of a circle, this tangent is perpendicular to the radius through the point of contact. A is the point of contact. This is the center. So through the point of contact A, we take the radius. Now this radius OA is always perpendicular. I shouldn't say is always perpendicular, is perpendicular. The radius through the point of contact is perpendicular to the tangent. That is, the tangent and the radius will meet at right angles. Circle, any point on the circle, the tangent at any point of a circle, any point, tangent, the tangent at any point of a circle. So through this point, we draw a tangent. Now this tangent through any point of a circle, this tangent is perpendicular to the radius. Which radius? There are so many radii. Which radius? Which radius? The radius that is drawn through the point of contact. The radius that is drawn through the point of contact over this one. The tangent and this radius are perpendicular to each other. This is the theorem. Let's see how to prove this theorem. For that, we need to go back to 9th standard. We need to recall a theorem from 9th standard from the chapter congruent triangles. But this part was deleted for you in 9th standard, so I thought we'll do it now. This is from that part, inequalities. Inequalities in a triangle. Inequalities in a triangle, which was deleted. So in that sense, you have not come across this in 9th standard. So we have to see it now. Consider a line L. Consider a line L. Now, supposing, yeah, there is a, let's take this point O. And, just say that there's a point A here, B here, C here, D here. All right, many. Now, supposing you are standing at A and you take this path to reach the point O. There's another person at B and that person takes this path to reach the point O. There's another person at this point C and that person takes this path to reach O. So like this, different people take different paths, but they reach O. They're all standing on the line L. There are some people standing on the line L, and they take different routes. All these people, they take different routes to reach the point O. They take different routes. Is my voice clear, children?
Yes, ma'am.
Okay.
Yes, ma'am.
All right. Now, all these people take different routes to reach O. They're all standing on the line L. A, B, C, D, E, F, G, H, I, and J are all standing on the line L. And they take different routes to reach O. So A walks along AO, B walks along BO, like that. Okay, so they take different routes. So this one walks like this, IO. You understand? Now, EO walks like this, and it so happens that EO is perpendicular. EO is perpendicular to the line L. And the theorem says that EO is the shortest distance. The perpendicular distance is the shortest distance from or between a point and a line. The shortest distance between a point. The point is not lying on the line. The point is outside the line. The point O lies outside the line. The point O lies out. Point is not on the line L. Then if the point lies on the line L, then the distance is 0. There is a line L. There is a point O that lies outside the line L. We are talking about the shortest distance between the line and this point. The shortest distance is the perpendicular distance. You can all, you can believe it, right? You wouldn't really have a big doubt in your mind. We'll see why it is the shortest distance. But you do understand from the length of the line segments, you do believe that, OE should be the shortest because it's a perpendicular distance. OE should be the shortest. It's easy to believe because the path OA is longer than the path OB, is longer than the path OC. Okay, now we'll see why the perpendicular distance. Children, in this case, we have to consider a line and a point lying outside the line. Let me do it again. Like the requirements. What are the requirements to understand this result? What are the requirements? Requirements: line L, point O, lying outside the line L. These are the requirements. What are we trying to, understand from this? We are first trying to find, we are trying to understand the different routes that can be taken to reach the line, to reach the point O from L. So from L, you can walk like this. Supposing you're on L, you can walk like this to reach O. You can walk like this to reach O. You can, if you're on L, you can walk like this to reach O. But this is the shortest distance. The perpendicular distance is the shortest distance. The perpendicular distance is the shortest distance between the line L and the point O. We'll understand how. So it's given that OA is the shortest distance. We'll take another distance OB. It's given that OA is the shortest distance between O and L. Between O and L, it's given that OA is not the shortest distance. OA is the perpendicular distance. Sorry. It's given that OA is the perpendicular distance. When OA is distance. You're given OA as the perpendicular distance is given to you. OA is the perpendicular distance is given to you. We need to understand why it's the shortest distance. Okay, so it's a perpendicular distance. So that means here we have a right angle. So which now what is OB? OB is not the perpendicular distance. It's some other distance. It's not the perpendicular distance. Now when you compare, so this is a right triangle. This is a right triangle. When you compare the length of the line segment OA and OB, OA is shorter because OB is the hypotenuse. We know that in a right triangle, the hypotenuse is the longest side. We know that in a right triangle, the hypotenuse is the longest side. So when you compare OA and OB, see first, how do we know it's a right triangle? Because we are given that OA is the perpendicular distance. Because we are given that OA is the perpendicular distance. It's given. OB is some other distance. It's not the perpendicular distance. OA is the perpendicular distance is given. So now OAB, in OAB right triangle, we have two distances between O and L. We have two distances between O and L. One is OA. That is, there are two paths. One path is OA, the other path is OB. OA path is the perpendicular distance. OB is some other distance between O and the line L. OA is the perpendicular distance between O and L. OB is some other distance between O and L. So since OA is the perpendicular distance, OAB is a right triangle. And we know that in a right triangle, the hypotenuse is the longest side. That means OA is shorter than OB. OA is shorter than OB. So like this, if you compare OA with any other distance, the same theory will hold good. It will be a right triangle. So if you take this right triangle, OAC, where you have the two distances OC and OA, OA being the perpendicular distance and OC being some other distance. OCA is again a right triangle. So when you compare the length of the line segments OC and OA, same result you will get. OC is longer than OA. So OA is shorter. So like that, when you compare OA, the length of the line segment OA to any other length, to any other distance, using the same idea, all of them will be the hypotenuse in the respective right triangles. All of them will be the hypotenuse in the respective right triangles. And everywhere you will get the result that OA is shorter. OA is shorter. That means OA is the shortest distance between O and L. That means OA is the shortest distance between O and L. Because everywhere you will get, when you compare OA with any other distance, you will get OA shorter than that other one. That means now when you compare with anybody else, OA is shorter, meaning OA is the shortest distance. So this says that the perpendicular distance is the shortest distance between a point and a line. Point does not lie on the line, children. Point lies outside the line. The result is this. The perpendicular distance is the shortest distance between a point and a line. Point not lying on the line. Line. So don't imagine something like this. Supposing the point O is here and supposing the line is here like this, is here like this. How will we find the perpendicular distance? Children, we are talking about a line, not a line segment. Because obviously if there's a point O here and there's a line segment here, line segment AB here, how can you draw a perpendicular? How can you draw a perpendicular from O to AB? Not possible. So you cannot draw a perpendicular from, from any point O and some given line segment AB. We're talking about a point and a line. Requirements, line L, point O lying outside the line L. We're trying to understand the distance between O and L. Between O and L, which is the shortest distance? That's what we're trying to understand. From L, if you want to go to O, which is the shortest route? From L, if you have to reach O, which is the shortest route? The perpendicular distance is the shortest route. So like this, you have many routes. From this line, if you want to reach O, you can go like this. If you're here, you can go like this. But who will reach fastest? This one will reach fastest because this is the shortest distance. So it's given that OA is the perpendicular distance. OA is the perpendicular distance. OB is some other distance between the point O and the line L. Now OAB, we are comparing two distances. We are comparing the perpendicular distance and this other distance in this right triangle. See, you will wonder why you're not taking AB, why you're not comparing AB. AB is not in our study at all. AB is not a distance between O and L. AB, the third side of the triangle AB, that's not relevant because that's not relevant to our study because that's not any distance between O and L. See, when you compare OA and OB, OA and OB, OB being the hypotenuse, we are only saying that OA is shorter than OB. We are not saying that OA is the shortest side of the right triangle. That we are not saying. We are not saying that OA is the shortest side of the right triangle. That we can't say. Comparing these two, OA and OB, since OB is a hypotenuse, OA is shorter than OB. Everywhere you will be comparing only with the hypotenuse, right? Everywhere you're comparing with the hypotenuse. In the respective right triangles, there'll be hypotenuse. So everywhere you will get that OA is shorter, OA is shorter, OA is shorter. Like if you take this right triangle, OAC, OAC, if you take this right triangle OAC, where OA is the perpendicular distance and OC is some other distance, OC is the hypotenuse. So hypotenuse is longer than any other side. So OA, OC is longer than OA. That means OA is shorter than OC. So when you come, all the other distances will be hypotenuses. All the other distances. Only this will be shorter than all the hypotenuses. So that means that is shorter than all the other line segments, which means it's the shortest distance. So the perpendicular distance is the shortest distance between a point and a line. And the converse is also true. And so if you take, let's see both now. Now if I say that OA, see, what should you look out for? Is there a line? Yes. Is there a point lying outside the line? Yes. Is there a line? Yes, there is a line L. Is there a point lying outside the line L? Yes, there is a point O lying outside the line L. Okay. Now I'm saying OA. I'm saying OA is perpendicular. What is OA? It is a distance. It's a path to reach O from the line L. OA or AO is a path to reach the point O from the line L. And I say that if I say that OA is perpendicular to L, that means OA is the shortest route. If I say OA is the shortest route, then it's perpendicular to L. If I say OA is the shortest distance between O and L, then it's a perpendicular distance. If I say OA is the perpendicular distance between O and L, then it is the shortest distance. The two terms are perpendicular and shortest. Perpendicular distance, shortest distance. If OA is perpendicular to L, that means OA is the shortest route between O and L. if I say that OA is the shortest route, OA is the shortest route from O to from L to O or between O and L, then that means it's a perpendicular distance. If it's given as a perpendicular, it is the shortest route. If it is the shortest route, then it's perpendicular. Now for this theorem, circle, tangent, point P is the point of contact, tangent say L, circle with center O, point of contact, through the point of contact radius. We need to prove that this is 90. We need to prove that this is 90. This is 90. So can we see the center of the circle is the point lying outside L? Bring in that situation here. The tangent is the line. The tangent is that line. And the center of the circle is the point lying outside the line. The tangent, we discuss something now. Relate that to this. The tangent is the line. And the center of the circle is the point lying outside the line. Now we need to show that this is the, to get 90 degrees here, we should prove that OP is the shortest distance, because we know that if it is the shortest distance, it's a perpendicular distance. If it is a perpendicular distance, it's the shortest distance. So since we have to prove that it's perpendicular, we need to prove that OP is the shortest distance from O to L. Both are the same, no? From L to O, O to L. We need to prove that OP is the shortest distance from O to L. How do we prove that? So let's take any other point. Now, on the tangent, how many points lie on the tangent? How many points lie on the tangent? Tangent is a line. The tangent is a line, right? Yes, ma'am. Yeah, so there are infinitely many points lying on the line L. The tangent is a line, and so there are infinitely many points lying on the line or the tangent. Of those infinitely many points, there's only one point that is in contact with the circle. On the tangent, there are infinitely many points. Of those many points, because the tangent is a line. Tangent is a line. There are many points. On the circle also there are many points. But this point P is the point that is common to the circle and the tangent. Point P lies on the circle. Point P lies on the tangent. Understand that? On the tangent, there are many points. There are infinitely many points lying on the tangent. Again, infinitely many points lying on the circle. There is one point which is common to the circle and the tangent, or there's one point which lies on the circle and on the tangent. There is one point that lies on the circle and on the tangent, and that is the point P. Okay. So now, as we said, on the tangent, there are many points. So let's take another point Q. So we now tell me, children, are there any points on the tangent that passes in inside the circle, going inside the circle? Now we know that there can be points lying inside the circle, on the circle, and outside the circle, right? There can be points lying inside the circle, on the circle, and outside the circle. Now, when you look at the points on the tangent, all the points on the tangent will lie outside the circle. except the point of contact P which lies on the circle. There is no point on the tangent. There is no point on the tangent that lies inside the circle. There is no point on the tangent that lies inside the circle. There is only one point on the tangent that lies on the circle. All the other points on the tangent lie outside the circle. This we understand. That's what is the definition of a tangent. The tangent and the circle will have only one point in common. So all the other points on the tangent cannot lie inside the circle. That's not a tangent. All of them will lie outside the circle. So if you take a point Q like this and join OQ. Let it intersect the circle at R. Now tell me, is OQ less than OR, or is OR less than OQ? Which is correct?
OR is less than OQ.
OR is less than OQ. Why?
Because OR is radius.
Because OR is a part of OQ.
Yes.
A part is always less than the whole. OR is a part of OQ because Q lies outside the circle. How do you know that Q lies outside the circle? Because it's a tangent. P is the only point that touches the circle. All the other points on the tangent will lie outside the circle. And when you join OQ, it intersects the circle at R. So OR is a part of OQ. When you try to join like this, see, this comes first. When you join like this, it intersects the circle. R comes first, and then you go on and you get OQ. OR is a part of OQ. So OR, all of you understand that OR is less than OQ. Now replace OR with OP. Can you replace OR with OP?
Yes, ma'am. Both are radius, so it can take place.
Yeah. So that means OP is less than OQ, right? OP is less than OQ.
Yes, ma'am.
Like this, if you take any other point like R and you join this, what result will we get? We will get OP is less than OR. So that means OP is the shortest. That means OP is shorter than any other line segment. OP is shorter than any other line segment. OR, OQ. You take any point on the tangent. OP is shorter than OQ, OS, OR. So that means OP is the shortest distance between O and the tangent. OP is the shortest distance, and we know that the shortest distance is the perpendicular distance. Therefore, OP is perpendicular to the tangent L, or the radius is perpendicular to the tangent through the point of contact. Excuse me, children. All right, children. So tangent T or L, point of contact P. Take any other point on the tangent other than P. We know that OP is the radius through the point of contact. OP or PO is the radius through the point of contact. We need to prove that OP is perpendicular to the tangent. For that, take a point Q on the tangent. So it's a point other than P. Take a point Q on the tangent and join OQ. As you join OQ, let it intersect the circle at R. OR is less than OQ. Replace OR with OP because OR, OP both radius. So OP is less than OQ. OP is less than OQ. Like this, if you take some other point on the tangent, say like V, and you join OV, you will get the same result. You will get the same result. OP is less than OV. You will get OP is less than OV. You take some other point, you will get OP is less than O. What else can I write? OM. You take a point M. OP is less than OM. If you take a point N here, you will get OP is less than ON. See, when you're getting OP is less than OQ, then everywhere you will get the same thing. OP is less than OQ. So OP is less than ON, OP is less than OM, OP is less than OV. So that means OP is the shortest distance. OP is the shortest distance because OP is less than all the other distances. OP is the shortest distance from O to the tangent. From O to the tangent. And we know that the perpendicular distance, the shortest distance is the perpendicular distance. OP is the shortest distance, and we know that the shortest distance is the perpendicular distance. Therefore, OP is perpendicular to T. Please go through this. We can see this again in the next class. I already shared these pictures, I think. Correct, children?
Yes, ma'am.
From the beginning, if you need to take a screenshot anywhere, please do it. If you need to take a screenshot, please do it. So this is about the spokes of a wheel. This is about the spokes of a wheel. This is about the spokes of a wheel. And this is the road. Assuming it's, plain. Assuming it's plain, the road. So each of these spokes will be perpendicular to the road. When they, come in contact with this point. The spokes of the wheel, when it moves on the road, I can't turn it over here, but you can understand that. The spokes of the wheel. So here at this particular point, this spoke, this one is perpendicular to the road, like radius perpendicular to tangent. That's what this figure is. Screenshot if you will need. Not a part of your syllabus. Yeah. The lengths of the tangent drawn from an external point to a circle are equal. The lengths of tangents drawn from an external point to a circle are equal. Circle, external point, circle with center O. And we know that there are exactly two tangents. There are exactly two tangents that can be drawn from an external point to the circle. So I don't know if I'll be successful. So through the point P, exactly two tangents can be drawn to the circle from the given external point P. Now we need to prove that the length of the tangents from an external point P to the circle are equal. So that's what I said, lengths of the tangents. Tangents are lines. Then how lengths of tangents? Lengths of tangents meaning lengths of the tangent segments. So which is the tangent segment here? So if you mark this as A, point of contact A, point of contact B, the distance between the point of contact and this external point, this is the tangent segment. AP is a tangent segment because P is a point on the tangent. You can see that P is a point on the tangent and A is the point of contact. So the length of the line segment between the point of contact, the length of the line segment between the point of contact and the and any other point on the tangent is the tangent segment, is the length of the tangent segment. Similarly, see here, point of contact, and you can see that this point P also lies on the other tangent. So this distance BP is a tangent segment. Tangent segment. The endpoints of a tangent segment are, one is the point of contact. The other is any point lying on the tangent. When you say tangent segment, it has two endpoints, right? So one endpoint should be the point of contact. Point of contact is one endpoint. The other endpoint lies on the tangent, any point on the tangent. So A is a point of contact. P is any point lying on the tangent. So AP is a tangent segment. B is the point of contact. P is any point on the other tangent also. So BP is a tangent segment. So we need to prove that AP is equal to BP. So for that we need to join the points of contact. Join A to O, the points of contact to the center. So join A to O and B to O. Join A to O, B to O, and also join OP. Join OA, OB, and OP. Now, OA is perpendicular to the tangent, to this tangent. OB is perpendicular to this tangent. Because OA is a radius. And this is the tangent through the point of contact A. So the radius and the tangent at the point of contact are perpendicular to each other. So this is 90, this is also 90. So when you take up these two these two triangles, this angle is equal to this angle 90 degrees. R, that is R. OP is the common hypotenuse. Why is it the hypotenuse? Because this is 90 and this is 90. So this will be the common hypotenuse. Opposite to right angle. Common hypotenuse and some other side, any other side. OA is equal to OB, radius. OA is equal to OB, radius. In the two triangles, this angle is equal to this angle 90 degrees. Why? Because radius perpendicular to tangent at the point of contact. Right angle, hypotenuse, OP. OP is a common hypotenuse. And then OA is equal to OB, radii of the circle. So RHS congruence rule, the two triangles are congruent to each other. CPCTC, PA is equal to PB. CPCTC, PA is equal to PB. Tangent PA is equal to tangent PB. Go through this one, children. I'll just get back. The next theorem. If two tangents are drawn from an external point, then if two tangents are drawn from an external point, then they subtend equal angles at the center and they are equally inclined to the line segment joining the center to that point. Circle, tangents. This is the center of the circle. This is that external point P. This is the line segment joining the center and the external point P. This is the line segment joining the center and the external point P. A point of contact, B point of contact. OA radius, OB radius through the points of contact. Now, this is the line segment joining the center and the external point. This is one of the two tangents. AP is a tangent or a tangent segment. AP is a tangent segment. You can see OP here and the tangent here like this. This is an inclination. This is an inclination. That is, this is the inclination of the tangent AP with the line joining the center and the external point. This one, this is the line or the line segment. See that words, you can say line segment. Yet the meaning is line segment here because there are two endpoints, O and P. It's a line segment. But sometimes if the word line is used, don't get confused. OP is the line segment joining the center and the external point P. OP is the line segment joining the center and the external point P. AP is the tangent. This is the inclination. This one is the inclination. This is the inclination of the tangent with the line joining the center and the external point. This is the tangent. How much the tangent is inclined. This is regarded as the baseline. This is like the baseline. How much this tangent is inclined with respect to this baseline. This is the inclination. This is the inclination of the tangent AP with the line or the line segment joining the center and the external point. Now see the other tangent BP or PB, and this is the line segment joining the center and the external point. This is the inclination. This is the inclination of this tangent BP with the line segment joining the center and the external point. See, when you're measuring inclination or some angle, there should be some baseline. There should be a baseline. The baseline is OP, and OP is the line segment joining the center and the external point. Now, the inclination made by the two tangents, the inclination made by the two tangents with the line segment joining the center and the external point are equal. That means this angle, supposing this angle is 20 degrees, this also will be 20 degrees. That explains the second one. They're equally inclined. That is the tangents. See the second point? They are equally inclined. That is, the tangents are equally inclined. That the angles are equal. They're equally inclined to the line segment, joining the center to that point. That point is the external point. The first one is they subtend equal angles at the center. These are the angles subtended by the tangents at the center. These two angles are equal. See, these results easily we get by CPCTC. We're just trying to understand them in words. Now, this is the tangent segment. AP is a tangent segment. This is the center of the circle. Now, we'll try to understand the angle subtended by the tangent segment at the center. The angle subtended by the tangent segment at the center. So to understand the angle subtended by the tangent segment at the center, you need to join the ends of the tangent segment to the center O. See, join A to O, join P to O. When you join like this and like this is the angle subtended by the tangent segment AP at the center O. This one. Because how do we understand the angle subtended by a line segment? Here the tangent segment. You should bring the ends of the tangent segment. A and P are the ends of the tangent segment. Pull it. Join A to O. Join P to O. This angle formed at the center is the angle subtended by the tangent segment AP at the center. Similarly, BP is a tangent segment. Join B to O and P to O. That's already there, but I'm just doing it over it. P to O. When you join B to O and P to O, this is the angle. This is the angle subtended by. This is the angle subtended by the tangent segment BP. The tangent segment BP at the center O. So if two tangents are drawn from an external point, then they subtend equal angles at the center. These two angles at the center are equal. They subtend equal angles at the center. The tangents subtend equal angles at the center, and they're equally inclined. They're equally inclined with the line segment joining the center and the external point. And I don't have to explain that these two can be got using congruence in triangles and CP-CTC. So show that these two triangles are congruent. CP-CTC, you will have this angle is equal to this angle and this angle is equal to this angle. Here I've used the SSS congruence rule. Actually, you can use, since you have a lot of information, here I've listed the equalities that satisfy the SSS congruence rule. You can also, if you mark maybe this one as 90 degrees and this one as 90, you can say this side, this angle and this side, you can say SAS, you can say RHS. This is what is conventional. This is what you will see in the books. But you can use anything. I'm saying like when you introduce 90 degrees, radius perpendicular to tangent. So 90 here and 90 here. You can make SAS, side angle side, or you can make RHS. SSS is conventional, what you see in the books. So you can see the 3 points, AP is equal to AQ, because now we know, we have proved that tangents from an external point of the circle are equal. So AP is equal to AQ. Tangents from an external point of the circle are equal. OP is equal to OQ, radii of the same circle. OA is equal to OA, common side. Triangles congruent, CP, CTC, you will have those results. All right, children, is that fine? Any questions, children? Class, use the emoji, raise your hand. Shakti, Shabari Grish, Hariharan. Okay, so we have Parkavi, Shriya, Aksharam, Shivani, Shruti, Srinivasan, Muttuvel, Arnav, Tirunesh, Sudarshan, Nafi, Nivedita, Rakshan, Balahari, Shakti, Shabarigrish, Hariharan. All right. Thank you, children. Any questions, children? Okay, others?
No, ma'am.
All right, children. Thank you. Yes, children. So I'm not doing the proofs first. We'll see how the results. Okay. So when we, solve, I think the last exercise in circles, you will be getting to learn many results on circles. I'm taking up the numerical versions based on the results, and then we'll see the proofs for them. All right. Now look at this. Children, is this 90 degree? Don't read the question. I'm telling you something else. In this figure, is this 90, children?
Yes, ma'am.
Yes, ma'am.
Is this 90?
Yes, ma'am.
So
Yes.
always these two will be 90, in a figure like this, that is where you have a circle and where you have two tangents from an external point, when you have a figure like this is 90, this is 90, always. Now you can see that this one is a quadrilateral. When you draw this figure, when you make a figure like this, that is circle, tangent from an external point, center, you will get a quadrilateral here. See it? Quadrilateral 1, 2. You can see a quadrilateral like this 1, 2, 3, 4 like this. Wherein this is 90, this is 90. Now we know that the sum of the four angles of a quadrilateral is equal to 360 degrees. So 360 is made up of two 180s. 180 plus 180 is 360. So of 360, this is 180. The sum is 180 already here, these two opposite angles. So the sum of these two angles also should be 180. The sum of these two angles also should be 180. The sum of these two angles also should be 180. So then the total will be 360. Circle, tangents from an external point of the circle, point of contact, radius, 90 degrees, 90 degrees. 90 plus 90, 180. 360 minus 180 is 180. So the sum of this angle and this angle, this one is a quadrilateral. 1, 2, 3, 4. 4 sides. It's a quadrilateral. So the sum of these two angles also will be 180. So now tell me the measure of x, children. What's the measure of x? What is the measure of x?
150, ma'am.
How? 180 minus 30, correct?
Yes, ma'am.
180 minus 30. Which is the quadrilateral here?
AOBP.
AOB. Yeah.
AOBP.
AOBP is a quadrilateral. Name the tangent segments.
AP and
AP and BP are tangents.
AP and BP. Which is the external point?
P, ma'am.
P. Name the points of contact.
A and B.
Which is the radius through the point of contact A?
OA.
AO.
AO.
OA.
Or OA. Okay. Which is the radius through the point of contact B?
OB.
OB or BO. Now OA. So as we understood, this is always 90. This is 90 in a figure like this. This is 90, this is 90. Sum of these two angles is 180. So the sum of these two angles also will be 180. So when you see a figure like this, x is 180 minus 30, 150 degrees. Now, can you give a special name to this quadrilateral OABP, OAPB?
Kite, ma'am.
It's a kite.
Kite. Okay, correct. Kite. Then it's a kite. Yes, because the two pairs of sides are equal. The two pairs of adjacent sides are equal. So it's a kite because OA is equal to OB. And then AP is equal to BP. So it's a kite. It's a kite. Two pairs of adjacent sides are equal. OA is equal to OB radius. And AP is equal to BP because tangent segments from the same external point. Or tangents from the same external point. Any other name? Any other name can you can give to this quadrilateral? It's a kite. Good. No?
Trapezium.
See, a kite is not a trapezium.
Ma'am, cyclic quadrilateral.
Yeah. Who's that? Shreya, is it?
Parkavi, ma'am.
Parkavi. Very good. Parkavi. It is a cyclic quadrilateral. Okay, let me bring the difference between a kite and a trapezium. In a kite, no pair of opposite sides are parallel. In a kite, no pair of opposite sides are parallel. In a trapezium, one pair of opposite sides are parallel. In a parallelogram, both the pairs of opposite sides are parallel. In a kite, no pair of opposite sides are parallel. In a trapezium, one pair of opposite sides are parallel. Parallelogram, both the pairs of opposite sides are parallel. And Parkavi is absolutely right. OAPB can be called a cyclic quadrilateral because in a cyclic quadrilateral,
Opposite sides are supplementary.
opposite angles are supplementary. Very good. Opposite angles are supplementary. Yeah. So here we can see that angle A plus angle B, opposite angles. A plus B is 180. Angle O plus angle P is 180. So OAPB is a cyclic quadrilateral. It's a kite. We are right. It's a kite. It's a cyclic quadrilateral. Okay. So children, we are not trying to just find the value of x. We are trying to understand some other details also. So please don't turn a deaf ear after understanding the value of x, understanding how to find the value of x. Please listen to everything. Okay, so x we all understood 180 minus 30 is equal to 150, which is the value of x. Now, the next part of the question. If OP is joined, okay, let's join OP. If OP is joined, so what do you call the line segment OP? OP is the line segment joining what and what? OP is the line segment. OP is the line segment joining the
Points 1.
no, it's not like
Center
okay.
and the external.
Center, yeah. O is the center. P is the external point. So OP is the line segment joining the center and the external point P. OP is the line segment. What do you call O? Center of the circle. Yeah, correct. Center of the circle. What do you call the point P?
External.
External point. So if you join the center O and the external point P, OP is the line segment joining the center O and the external point P. So join OP. All right, we joined. Now find BOP, which is BOP. BOP, this one. BOP, children, this one. Children, this angle, BOP. And angle BPO. BPO, this one. Now quickly tell me, who can tell me? What's the, let me call it Y and Z. What's the measure of Y? Fast.
75 degree.
75 degree.
75. Very good. What's the measure of Z?
15 degree.
15 degree.
15 degree. So how did we get them? Using these results. CTC or what we just saw, the theorem which we just saw. In this theorem, we understand that these two angles are equal, these two angles are equal, and also these two angles are equal. They subtend equal angles at the center. They subtend equal angles at the center, and they're equally inclined to the line segment joining the center and the external point. So if you know this full thing, divide by 2. If this full thing is 60, 30, 30. If this full thing is 120, this full thing is 120, 60, 60. So this one, because the full thing is 150, the full thing is 150, this will be 75. This full thing is 30, so this will be 15 degrees, half of it. And the angle sum property will hold, would see this 90. 75 and 15 is 90, 90 plus 90, 180, triangle. What's the value of x, children? From the beginning, what's the value of x?
150 degrees.
180 minus 30, 150 degrees. We'll join OP. BOP. BOP is this angle. What's the full angle? What's the measure of the full angle? AOB?
150.
AOB is 150. So this angle BOP will be 150 by 2, 75 degrees. And BPO, this portion BPO. This full thing is 30 degrees. So 30 by 2, 15 degrees. Okay. Oh, I've forgotten to answer that. I've only answered X, I think. Okay, fine. Let me just tell you how to work it. So once you find, when you write angle BOP, you must say it is 150 by 2, 75 degrees. And in the bracket, you must give that reason. Equal tangents are equal tangents subtend equal angles at the center. Then let me do it slowly, 1 minute. I think make a note of this in your book, children, since it's not there. Now you will say after finding 75, I'll use angle sum property and find why should I give such a big reason. You can do that also. After finding this is 75 degrees, my God, for this I have to give such a big reason. I'll use angle sum property. 90 plus 75 is 165. So this is 15 degrees. You can do that also. There's no hard and fast rule that you should use a theorem. Anyways, any property which can be justified. Is it okay, children?
Yes, ma'am.
Can we go to the next one?
Yes,
Okay. All right, children. Okay. So here we have to find AD. You can see that the quadrilateral ABCD, you can see that the quadrilateral ABCD circumscribes the circle with center O. The quadrilateral ABCD circumscribes the circle with center O. Now there's a very interesting property. In such a case, when a quadrilateral circumscribes a circle, the sum of its opposite sides are equal. That is, which are the opposite sides of the quadrilateral? Tell me the opposite sides of the quadrilateral.
A, B, and C.
A, B, and C, D. What is the sum of the opposite sides?
10 centimeters.
12.
No, not numerically. What is the sum of the opposite sides? How do you write the sum of the opposite sides?
AB plus CD.
AB plus CD. Which are the other pair of opposite sides?
AD and BC.
BC plus AD.
BC plus AD or AD plus BC. The sum of the opposite sides are equal. See, I told you, all this is in the exercise in NCRT. We'll prove all these results. I'm not forcing you to believe them. But before we do the proofs, I thought we'll do the numerical versions. We'll see the applications and then see the proofs. So the property is this. When a quadrilateral circumscribes a circle, the sum of its opposite sides are equal. The sum of its opposite sides are equal. The sums are equal. Which sums? The sum of the opposite sides are equal. AB plus CD is equal to AD plus BC. When a quadrilateral, the quadrilateral is outside, the circle is inside. Then the quadrilateral is outside, the circle is inside. That is, the circle is inscribed in the quadrilateral. Circle is inscribed in the quadrilateral. The quadrilateral circumscribes the circle. The sum of the opposite sides of the quadrilateral are equal. So AB plus CD is equal to AD plus BC. Now how do you find? So AB is 4 centimeters plus CD is 8 centimeters is equal to AD we don't know plus 7. Work this and find. So 12 minus 7, 5 centimeters. So AD is 5 centimeters. See, what a lovely property. AD is 5. If you simply have a quadrilateral, this property does not hold good. For a quadrilateral like this, some of the opposite sides are not equal. Only when that quadrilateral can circumscribe a circle. This is sorry. Is this understood, children?
Yes, ma'am.
Okay.
Yes.
All right. I think you can take screenshots and complete it, children. I don't know if you did it. This is the first one. Second. we'll wind up the class with this one. Again, here you see that a quadrilateral circumscribes a circle. A quadrilateral circumscribes a circle. So here the opposite sides subtend supplementary angles at the center. That's the property. It should be like this. A quadrilateral circumscribing a circle, or a circle inscribed in a quadrilateral. A circle inscribed in a quadrilateral. When a circle is inscribed in a quadrilateral, or when a quadrilateral circumscribes a circle, the opposite sides subtend supplementary angles at the center. The opposite sides, AD and BC. Let's take up AD and BC first. What angle do they make at the center? So, as I always say, when you take up the side AD, join D2O, A2O. This is the angle subtended by AD at the center. Take the other side BC. Join B2O, C2O. Why O? Because center. B2O, C2O. This angle is the angle subtended by BC at the center. Similarly, this is the angle subtended by AD, side AD at the center. This is the angle subtended by side CD at the center. The opposite sides subtend supplementary angles at the center. That means x plus 185 is equal to, see, this is the angle subtended by AD. This is the angle subtended by BC. Opposite sides are AD and BC. And these are the angles subtended by the opposite sides. They are supplementary. X plus 85 is 180. So x is equal to 95 degrees. The side AB subtends this angle. The side CD subtends this angle. The sum of these two angles will be 180. The sum of these two angles will be 180. The sum of these two angles is 180. These two angles is 180. So totally around the point we'll have 360 degrees. Is the property understood, children?
Yes, ma'am.
Okay. When a quadrilateral circumscribes a circle, its opposite sides subtend supplementary angles at the center. So AOD plus BOC is equal to 180. X plus 85 is 180. X is 95 degrees. Children, please complete all this in your classwork by the next class. Please complete all this the classwork by the next class. All the theorems and these three answers. Draw the figure and work the answer. All right, children. That's it for today's session. Thank you so much. Good night.
Thank you, ma'am.
Thank you.
Thank you, children. Thank you.
Thank you, ma'am.
Thank you, children.